today. And the topic for my presentation is high temperature chemical heat pump system and alloy selections, characterizations, simulation, and experimental development. And this topic is based on the funded project from IBRC and Innote UK. And my name is Yunting Ge, and I'm from London South Bank University, and Xin Zhang and Arten Maroki are researchers in my research team. So for this project, I would like to give a brief introduction about the background and also the research objectives. So for the background or motivations of this project, as we know in the UK, and heat accounts for about 1/3 of the nation's greenhouse gas emissions. And also because of global warming and cooling demand is increasing gradually. And it is now the fastest growing end-use energy demand in buildings. So to meet the government's ambitious target of net zero greenhouse emission by 2050, so essential to decarbonize the energy provision of heating and cooling. So to achieve this target, so what we do, so we will try to use maximally the zero or very low emission energy vectors such as renewables, and also the waste heat recovery from industries. So here you can see from this slide about the research objectives and the method. So what we do, we utilize a very low grade heat source, waste heat source, about temperature is about 40 degrees C. And also in industry, we can find out a lot of medium temperature heat source with temperature about 230 degrees C. So with these two different grade heat source, we utilize what we call the advanced technology, you call it the chemical heat pump. Actually, it is a metal hydride heat pump system to produce heat output with temperature about 130. And this heat output can be used for the heat network and to be used for the remote the heating by the end user. So once we produce the heat output with temperature about 130 degrees C, and we transport this heat through long distance pipe work and to the end user by means of the similar technologies. And at the end of the end user, so we utilize some energy conversion technologies. So we convert this transported hydrogen and also the energy into heating and cooling. So this is the research objective and also method used in this project. So the main technology utilized in this project is what we call the metal hydride heat pump. So I just give a brief introduction about the metal hydride heat pump system. So to explain it clearly, so I compared the metal hydride heat pump cycle with the conventional absorption heat pump cycle. So absorption heat pump cycle is the system layout is shown in the left side of this slide. And it includes 4 main components we all know about: the generator, condenser, evaporator, and absorber. So the high temperature heat source is used to heat up the generator, that one, yeah, and also the refrigerant such as water is evaporated out with high pressure and condensed by the condenser. After that, the working fluid is expanded, and the temperature and the pressure will be both decreased. And inside the evaporator, the absorb the heat from the low-grade heat source, that one produce cooling, it depending on the application of this absorption heat pump. And the water is evaporated out and absorbed by the absorber and also the we call it strong solution from the generator, and the weak solution will pump back to the generator. So this is actually the working mechanism for the absorption heat pump, that one. Yeah. So you have a high grade heat source input QH and low grade heat source QL input to the evaporator, and you can produce two medium grade heat output QM1 and QM2 with temperature about Tm. So this is the working mechanism for the absorption heat pump system. For this metal hydrate, so in the right side of this slide, I think it's quite similar to the absorption heat pump system. And let's look at the system compositions. It consists of two actually identical, we call it identical metal hydrate reactor pairs. That one, yeah. For each metal hydrate reactor pair, it consists of two reactors. The first one we call it high temperature reactor. We give it a name MH1, and the second one is the low temperature metal hydrate reactor. We call it MH2. That one, yeah. So inside each reactor is charged with metal hydroalloy and also absorb the hydrogen, that one, yeah. So if the high grade heat, QH heat up the high temperature reactor MH1, the hydrogen will be released out. So by means of the condensation pipe between these two reactors, hydrogen will travel from MH1 to MH2 and absorb MH2. In the meantime, the heat is released and with temperature about Tm. So similar to the absorption heat pump system. So in the meantime, for another metal hydrate pair, that one, yeah, the low grade heat will heat up the low temperature metal hydrate reactor, and hydrogen will be released out and absorbed by the high temperature reactor MH1B. And in the meantime, the heat with temperature about Tm will be released out. So what you can see for this metal hydrate heat pump system, it consists of two half cycles. For each half cycle, you have the high pressure operation with high grade heat input and the medium temperature heat output. And you have low pressure operation on the bottom side, and you have low grade heat input and have a medium temperature heat output. That, yeah. For the next half cycle, what you need to do to continue to produce a medium temperature heat output, you just swap the heat source, high grade heat source and low grade heat source to different reactors, and also the heat output as well, so that the system can operate continuously. So I think this just I give you a brief introduction about the difference between these two heat pump systems. So here I just give a summary about the comparison of these two heat pump cycles. So for absorptions, that one cycles, so heat pump cycle, we utilize two types of working fluid consistently, yeah, either water or ammonia. For the metal hydrate heat pump, the working fluid is hydrogen, that one, yeah. And for the absorption heat pump, and it has the absorbent, either depending on what type of absorption heat pump is used, it can be either lithium bromide or water, yeah, water. And for the metal hydrate, it uses metal hydrate alloys such as this LaNi5 or titanium and iron as absorbent. And the energy input is similar. We both are using the thermal energy as the energy input, not the electricity. And for the heat pump COP is also similar. Similar is about 1.2, depending on operating condition, 1.20 to 1.3. And but the dimensions for the whole thing for the same heat output, that one, yeah. So the dimension has a significant difference, that one, yeah. So for the absorption heat pump, I think the overall size is quite large compared to the I think for the metal hydrate heat pump is quite compact. And regarding to the heat output temperature range, that one, and for the absorption heat pump is limited. So you normally, depending on the heat source temperature, of course, but it has a limited heat output temperature. But for the metal hydrate heat pump, it can have a larger temperature range for the heat output. So this just will give a brief introduction about the chemical heat pump with metal hydrate alloy. So, and as we discussed, I think the metal hydrate alloy is the absorbent usable in the metal hydrate, and also the hydrogen is used as working fluid in the metal hydrate heat pump. So you can see in this slide, I think for the convenience of the transportation for these alloys, and normally it form like a alloy sheet like that. But before you charge the metal hydrate alloy into the reactor, you have to make it into we call it alloy powder with the size of about 50 μm and also 1 millimeter. That one you can use a specific device to make the alloy sheet into alloy powder, such as the ball milling machine to do it. So for the metal hydrate heat pump, I think the main operation is the chemical reaction of absorption and desorption. That one for the system. So once the hydrogen is reacted with metal hydrate alloys, that one, yeah. So you can produce a metal hydrate alloy, that one, yeah. And in the meantime, you can release the heat to outside. So the chemical reaction can operate in the opposite direction. So if you apply the heat to metal hydrate alloy, so the hydrogen will be released out, and you can produce the can produce back for the metal hydrate alloy. So on the bottom, you can see the graphic here. So here the metal hydrate, we call it the metal crystal, that one, yeah. And above is the metal hydrate. Above is the hydrogen gas, that one, yeah. So because of the pressure difference from hydrogen gas and the inside of the metal crystal, so the hydrogen will be, I think, so actually form a solid solution inside the metal crystal. That in the meantime, the heat is released out. So if you heat up this metal hydrate, that one you see, and the hydrogen will be released out, and this is like that. This is for the hydrating or dehydrating reaction process. So for this project, so what do we do? So by utilizing this metal hydrate heat pump, so what we want to do, we want to convert low-grade heat source with temperature about 35, and high-grade heat source with temperature about 230. I think by means of the metal hydrate heat pump system, we can produce 130 degrees C heat output. And as we know, in the energy-intensive industry, you can find out, I think, plenty of the heat source with temperature about 35. For example, the power plant, the cooling water system, and also 230 degrees low-grade heat from the energy-intensive industrial side. So this, you may say that 230 can be used to produce power by means of power advanced thermodynamic power cycle, such as the organic Rankine cycle. But I think the efficiency is quite low. So if you're using a heat pump system to produce heat output with temperature about 130, so this 100 degree heat output can be used for the heat network. And so we utilize metal hydrate heat pump instead of using the electric heat pump or absorption heat pump. So one reason is as we mentioned, they using the thermal energy as a heat energy input, and also they are using environmentally friendly working fluid of hydrogen. And the system is more compact compared to the absorption heat pump system. And more importantly here is it can have a high temperature range, I think larger temperature range for the heat output. So to do this, to achieve this target, I think there are some challenges to be addressed. So first challenge is to identify what type of metal hydride alloys can be used in this system, so meet the operating conditions of this. And in the meantime, once we have identified the metal hydride alloys, so we need to do characterizations for the metal hydride alloys so that we can utilize this metal hydride alloy properly in the system. And after that, I think that we need to develop a test rig for this system so that we can investigate experimentally for the system. And also we need to develop a detailed, I think, mathematical model for the system. So for the future application, if we want to enlarge, we want to scale up the system for actual application. So we need to develop a detailed modeling for the whole system. So if you are in this area, you will find out there are thousands of metal hydride alloys can be used in different energy conversion systems. But for this particular system, we need to identify the appropriate metal hydride alloy so that it can operate based on the operating condition. So similar to the refrigerant or refrigerant used in the refrigeration system, that one. Yeah. So to utilize the refrigerant properly in a refrigeration, we need to know the properties of refrigerant. So we need to know about the relation of the pressure, entropy, and also the entropy and the temperature and so on. For the metal hydride alloy, you can do the similar things. We call it characterization of metal hydride alloy. So we need to know the relations between the pressure, temperature, and the concentration of the metal hydride alloy and also the metal hydrate. So to show the relationship between the pressure and the temperature and also the concentration, it can be shown in this thing. So we call it PCT profile, in this diagram. So for this PCT profile, you can see some lines in this PCT diagram, that one, yeah. So on the top, this point, similar to our refrigerant, that one, this is we call it the critical point, that one, yeah, critical point. So from the critical point, you have a dot line here, like a dome line, that one, yes. These two lines can separate the whole region into 3 regions, similar to the refrigerant liquid two-phase and the vapor. And here, but we give it the name of alpha region and the alpha plus beta region and the beta region. So the difference for the alpha region here, so once the gas hydrogen, that one, yeah, absorbed by the metal hydrate, it forms we call it a solid solution. Actually, the hydrogen is solidified once the hydrogen is absorbed by the metal hydrate within the alpha region, that one, and in the metal crystal, that one here. So for this region, it's slightly different, that one. In the central region, alpha beta, that one, yeah, and the hydrogen in gas state is dissolved in the solid crystal of both metal and the metal hydrate here. And the beta region, yeah, that one is the beta phase is a solid solution of hydrogen in the metal hydrate crystal here. So normally for any metal hydrate energy system, so the metal hydrate is operating in alpha plus beta region, that one, yeah. So another difference is for alpha region, that one. So if you want to absorb limit specific amount of hydrogen, you need the metal hydrate pressure need to increase significantly. And similar to the beta regions, that one. So if you want to absorb a small amount of hydrogen, that one, yeah, the hydrogen pressure, the metal hydrate pressure will increase significantly. But within the alpha plus beta region, that one, even you have a larger absorption of the metal hydrogen, so the pressure just increase slightly, that not that much, that one, yeah. And also you can find out some solid line and dotted line, that one, at the same temperature. We call it isothermal lines, that one. Yeah, you can see here, T1, T2, and T3. And T3 is greater than T1, T2 and T1, that one. Yeah. So the solid line, we call it the absorption line, that one. Yeah. And and this one, this is, we call it the desorption line. That one, yeah, desorption line. Here, so in the middle point of this alpha and the beta region, if you draw a line to here, and you can see another diagram here. So this diagram shows you the relation between pressure and temperature. You can see the log pressure has a linear relation with the one result product of temperature here. And the delta H is the reaction entropy, and delta S is reaction entropy. So this diagram is called, sometimes we call it one Hoof relationship, that one for the metal hydrate. This is just, so once we have identified the metal hydrate, we need to know, to find out the details, I think, profiles of pressure, temperature, and concentration, so that we can characterize the selected metal hydrate alloy. So first, I think it's an important step for the application of the metal hydrate heat pump. So we need to identify the metal hydrate alloy, so that it can be utilized in the metal hydrate heat pump system and operate at the designed operating conditions. That one, yeah. So how to do that? So we utilize I think, some basic functions in the system. That one, yeah. So this is the system layout, and this is the cycle for this metal hydrate heat pump. You can see here, this cycle, the operating condition, the high temperature heat source. The high temperature heat source, it has a temperature range from 180 to 220 degrees C, and the low grade heat source has a temperature range from 25 and 45 degrees C. That's one, yeah. And the heat up temperature is between 120 to 140 degrees C. So you can see the system operates in two pressure levels. High pressure levels, the heat input to the high temperature metal hydrate reactors. That one, yes. So the hydrogen will be released out and flow into that reactor. That one, yeah. The low temperature reactor, and release the heat and absorbed by that low temperature reactor. So the low pressure operation, that one, the low grade heat is added into the low temperature reactor, and the hydrogen will be released out and absorbed by the high temperature reactor and the heat is released out at temperature about 130 degrees C. So during the operation of the high pressure operations, desorption, absorption, and in the end, what we found out, in the end, the pressure at point A will be the same at point B. So there is no further desorption and absorption. Similarly, for the low pressure operations, in the end of this operation, desorption and absorption, the pressure at point C and the pressure at point B will be the same, so that no further desorption operation operated. So based on this, that's one, and this is the basic chemical reactions, and this is the relationship between pressure and the temperature at each cycle point A, B, and C, D. So if we know temperature, we can carry out immediately about the pressure. And this two, that one, as I mentioned, this is for the high pressure pressure balance for this A and B. So in the end of the operation, the pressure point A is the same as the pressure point D. And for the low pressure operation, at the end of the operation, the pressure at point C and the same of the pressure point D. So to facilitate the metal hydrate alloy selection, so we use some variable, that one, theta and delta, that one. This variable is characterized the reaction, this formula. And this delta is calculated by means of this formula, that one, yeah. So to replace these two variables into these two pressure balance equations, we obtain this. So this is used, so later we can see, it can be used for the purpose of metal hydrate selections, that one, yeah. So this formula you can see here, you have two variables, theta and delta, that one. You can TH is the high grade heat input temperature, and TM is medium temperature heat output. Yeah. So if I have a constant temperature of Tm and Th, so you can see the linear relation between theta and the data. Yeah, and similar to this. Yeah. So we use this to identify the applicable metal hydride alloy. So to demonstrate this method for the metal hydride alloy, so what we do, we just select we select we call 82 metal hydride alloys, yeah, to just demonstrate the method for the metal hydride alloy selections, yeah. Of this 82 metal hydride alloys who are listed here, that one is here. So we classified them into two groups, that one. So one is high temperature metal hydride alloy, that one, yeah. One is a low temperature metal hydride alloy. So if the operating temperature is 35, and then we can calculate out the pressure of the metal hydride alloy, that one, yeah. So if the pressure is less than 1 bar, so we group them into high temperature alloys. So at the same temperature 35, if the operating pressure is higher than 1 bar, that one, yes, so we group them into low temperature metal hydride alloys, that one, yeah. So you can find out in the end. So of the 82 metal hydride alloys selected, so you have 30 high temperature alloy and also 52 low temperature alloys. So each high temperature alloy can be paired with one low temperature alloy. So together we can form about 1,560 high temperature and low temperature pairs, which can be used for the metal hydride heat pump system. So if we draw this into this diagram, you can see a lot of, I think, circles. That one, this circle, each circle represent one pair of metal hydride alloys. That one, yeah. So if we draw a line here, so you can see more or less a linear relation. But this is also what I found. That one, yeah, it's a linear relation for all these metal hydride pairs. That one, yeah. So how to identify the appropriate applicable metal hydride alloy pairs? So we use here these two formula. Yeah. So if you remember, this formula is from the pressure balance on the high pressure side, and this formula is from the pressure balance for the low pressure side. That one, yeah. So we're still using the previous diagram. This is the theta. The formula is calculated as this. This is the delta. That one, yeah, the ratio of reaction entropy. So if we have a constant 120 degrees C for the heat output Tm for this one, so but the Th, that we know Th has a range from 180 to 220. That one, yeah. So for each temperature, for example 180, we can draw a line, yellow line here, yeah. So if we have a 220, that is a purple line. That is a brown line. That one, you can draw another line here. So similarly for this, if we're using this formula, so and as the constant Tm, so we can have two values of TL. One is 22. We can draw one line here, green line, and this is a blue line with temperature TL 45. So this four lines draw in the same diagram. You can see the solid circle are enclosed into these four lines. So this will meet this can be applicable metal hydride alloys to be used in this metal hydride heat pump system. So if we do the similar things, we just increase the heat output temperature to 130. That one, yeah, you can see less metal hydride alloy pair can be selected. So solid circle line. So if you further increase the heat output temperature to 140, that one, yeah. So you can see very few, I think, metal hydride applicable metal hydride pair can be selected. So this is the method. So we summarize the selected metal hydride alloy into these two tables. The first table is with the medium temperature 130 degrees C, and the second one is with the heat output temperature at 140 degrees C. So for the temperature at 130, we can select about 28 applicable metal hydride alloys. For the TM at 140 degrees C, we can select about 12. So the red is included with the red square, that one, yeah, it is here. So since both, so this pair can be applied for both medium temperature, 130 and 140. For this metal hydride alloy pair includes by the blue line, that one can be used for both TMs, that one, yeah. So we identified two candidate metal hydride alloys, that one. One is included by the red square, and one is included by the blue square. So then after this, so we want to select only one, that one, yeah. So what we do the energy analysis, that one, to calculate out the COP for the heat pump, and also the Carnot COP, and also the active, we call it active COP, that one, yeah. So we choose the maximum one. So and then we calculate out that one for each applicable pair for this from this table, and this one from this table. So which one to select, that one? So for this red color one, that one, yeah, and the blue color one, I think the efficiency is more or less quite similar in terms of first law of thermodynamic efficiency and the second law of thermodynamic efficiency is quite similar. But you can see if you compare the operating pressure for the first pair and the second pair. So the first pair has a quite low operating pressure, that one, yeah, operating pressure, compared to the second one. So in the end, so we finally select these two metal hydride as a working metal hydride working pair, that one, yeah. So one is this, one is that. This is for the high temperature reactor, and this is the low temperature reactor, to identify that. Yeah, so I need to speed up a little bit. So the second part, once we have identified these two metal hydride alloys, so we need to do the characterizations of these two identified metal alloys, so that we can draw the relations, the PCT profile similar to this. So of course you can produce to characterize this metal hydride alloys by means of measurement only. But this will take quite, I think, this is not an easier job, that one, since so each, I think, isotherm lines, you need to measure up, I think, more than 100 points, that one, yeah. So that will take a longer time to get the measurement result. So, and also maybe you can use the modeling development only, but I think to make an accurate modeling, you have to validate with measurement. So what we do, we combine these two methods together. So we utilize some limited measurement result, and we develop, I think, a model for this PCT profile. And we validate this model with the limited measurement. And once we validate the model, so we use the model to characterize the selected metal hydride alloy and to draw the PCT profiles like this. So as we explained before, for each metal hydride alloys, and its PCT profile can be divided into two regions, alpha, beta, and alpha plus beta. Yeah, that one here. So we're using different formula, that one, for each region. For example, for this alpha plus beta region, since it's a linear relation between pressure and the temperature, and also on the concentration like this, so we're using this formula to model the metal hydride within the alpha and the beta region for both desorption and absorption process. And for the alpha and the beta region, you can see the curve are similar. So we're using the similar formula to model the PCT profile in this region. But there are some coefficients. That one is like for this formula, I think the A and the gamma, and also the V, and also the H. So this coefficient will be correlated by comparing between the modeling result and the measurement. Similar for the alpha region, you can also see some coefficient, such as the reaction coefficient, reaction entropy, and the reaction entropy, and also the median value of the concentration and also slope factor. So all these coefficients will be correlated when the model simulation result compared with the measurement, corresponding measurement. So for the critical point calculation, that one, you know this formula to calculate out the pressure if temperature is low for the absorption process, and also at the same temperature, you can also calculate out the pressure at the desorption process. So the critical point, so when the temperature increase to the critical point, these two pressure will be the same. So at this condition, so we can calculate out the critical temperature, and also after that we can calculate out the critical pressure. And you see another side, there's dome curve here, that one. So we also need to characterize that. So what we do here for this dome curve, we just simplify it into this dome curve. We're using this formula to model this dome curve, that one, a dome curve. And there are three coefficients, A1 and A2 and A3, and then we will correlate it out by comparing with the measurement result. So these two mitohydrolytes are the mitohydrolyte we have already identified by the method we have just introduced. And we compare the measurement result. See the symbols are the measurement result at different temperatures. This is for the absorption, and also this is for the another mitohydrolyte, and during the desorption process. You can see the model match quite well with the measurement result. That one, and this is the dome line, and this is the critical point, and the alpha beta region. So, and then we can, by comparing between the correlation and the measurement result, so we can find out the coefficient, and we want to correlate it. That one, this is for the alpha plus beta region, that one here, and the coefficient here, and also the critical temperature and pressure for each mitohydrolyte, that here. And for the alpha beta region here, you can also correlate out to these four coefficients, for different mitohydrolytes. And here, this is for the dome curve for the three coefficients, A1, A2, A3, that one here. And also we just gave some accuracy analysis when compare the simulation with the measurement. I think the model match quite well with the measurement. So to utilize this model for the PCT profile calculation, so we identify 2 points. That one for each isotherm lines, that one, So this point, so if, for example, the concentration is less than this C minimum, that one, so we can using two formula to calculate out the pressure. So you can using the formula used to calculate the pressure at the alpha region and also alpha plus basin to just compare these two values, that one. If to select the minimum value, that one, for the two calculations, that one, If at the same temperature, if the concentration is higher than the C maximum, that one, then you can using two formula to calculate out the pressure. That one. One is using the formula for the alpha plus beta region, one is for the beta region. Such as the final value is the maximum value between these two values. This is just to show you how to utilize this model. And after that one, we have developed mitohydrolyte heat pump system, that one. So as this. So I think it's quite complicated, and you can see the system layout for this test rig. I think this is simplified one, that one, And you can see two reactors, and so here, this one, tube-in-tube reactors, that one, you can have a pipe connection to the hydrogen pipe connection from from one reactor to another, to the second one. This one, this is reactor here, here. You can see and also this is the heat transfer fluid pipe connection port, that one, connects to the heat transfer fluid. We utilize the thermal oil as a heat transfer fluid to simulate the high temperature heat source and also the low temperature heat source, and also the medium temperature heat sink heat sink, that one. And we're using thermostatic baths. I think you can't see here. We're using 3 thermostatic baths here. You can see here. So one is for heating, another for low temperature heating, that one. Yeah, and in the middle is the heat output for the heat sink. And this is 2 metal hydrogen reactor connected by hydrogen pipe. That one. Yeah. And you can see some measurement device with temperature and pressure to measure the temperature and the pressure of the hydrogen and at each reactor site. And also you can have some, I think, safety protection devices. We have 2 pressure switch valves. And also it hasn't been shown here. You have 2 pressure relief valve. Pressure relief valve. And also you have some I2 vessel here just to store the hydrogen produced by the electrolyzer, and also the vacuum pump that's used to vacuum the whole system before the measurement process. And you have some 3-way valves just to direct the hot thermal oil to each reactor. So this is just the system layout. And this test rig has been developed and built, and it is allocated in our purposely built hydrogen lab at London Southbank University. So if you are interested, you're welcome to visit to see it in the future. So I just show you quickly about this test rig, the operation test rig, and this is for the low operation from C to D, not a metal hydrogen heat pump. So this is reactor A. This is we call it the low temperature reactor, and this is a high temperature reactor. That one here. So you see the low grade heat output. That one, the heat source. That called the thermostatic bath. Heat is up. That one, yeah, and the hydrogen will be released from this reactor to the second reactor, and second reactor just cool it down by means of this. We call it a medium temperature heat sink. That heat sink to produce heat output. So this is just to show you the operation. There is another operation is how we call it high pressure operation, just the opposite. So once from previous operation, the hydrogen is stored in the high temperature reactor. So we need to release it out by adding the high temperature heat source. This is the TB1. That one. It heats up, and hydrogen will be released out and will be absorbed by the low temperature heat valve, and the heat is released to the medium temperature heat sink to produce the medium temperature heat output. So this is our hydrogen lab. So I think we call it purposely built. So we have a ventilation system to ventilate the whole lab if it's any hydrogen leaked out of the system. So we double speed we have a double speed ventilation fan to exhaust out the hydrogen to the outside. And also we have some pipe connection. This is just for the hydrogen leaf pipe, vacuum pipe, and also the argon purging process, and also some safety issue, safe connection pipe, that kind of things. And this is the test rig that one here. So actually we have 2 test rigs. This is for the metal hydrogen heat pump, and we have another one is we call it metal hydrogen compressor that one here. So I can see here, I can lay out some ventilation pipe and so on. You see the lighting here. So all the facility and equipment inside this test rig lab is we call it A-type rated, and suitable for the hydrogen application. And this here you have argon gas connections, pipe connection. This is used for the purging process at the beginning of the test, after test. And this is the outside. You can see the ventilation duct here, ventilation safe for the hydrogen lab, here the hydrogen lab, and also some pipe connection, ventilation pipe connection to the outside. And underneath this one, this is the room for us to install the control panels and also the gas detection alarm and fire alarm and so on, and the ventilation system controls. So this is just for the operator to operate the whole test rig. So once the rig is installed, so we're using the control panel to automatically control and operate the test rig. So, and for the second rig, we have done some pressure test, and we do the pressure test up to 400 bar. And since for 400 bar, I think the test rig can stand that high pressure. As you see, this is the pressure test results. That one, this is for the oil circuit. Oil circuit, the pressure test is for 15 bar. I think you can see the pressure can stabilize for about half an hour. So there's no leakage for the oil circuit. And for the hydrogen circuit, I think you can see the hydrogen can be maintained at 400 bar, that one, yeah. So because of time, I go quickly, that one, yeah. So we slowly will produce some experimental result, but before we can get any experimental result, and we have developed, I think, detailed modeling for the whole metal hydrogen heat pump system. So we utilize the CFD method to develop models, that one, yeah. So this is the reactor, that one, yeah. So because of chemistry, that one, we just simulate half of the reactors, that one, A and B, that one, yeah. And this shows you the half cycle of this reactor pairs. This is for the first half cycle solid line, and this is the first half of solid line for the high pressure and low pressure operation here. And this is the dimensions for these two reactors. This is the actual direction we have designed and built and installed in the test rig. And this, I think, just some equations utilized for the CFD modeling. So we just don't go for that details. And this, I think, because of time, I just go quickly. This is some energy balance equations for the COP calculation and the heat input and heat output, and also we call it the specific heat power calculations. So for our system evaluation and also comparison and also optimizations, that one, yeah. So we validate the CFD model by comparing our measurement result, simulation result with a measurement, that one, yeah, by a simple metal hydrogen reactor for the absorption process. So this is the temperature profile, counter profile for the absorption process. That one, you can see the time variation from 10 seconds to 3,000 seconds. You can see the temperature at the beginning to increase quickly and then slowly going down to the cooling medium temperature. So what we do to validate the model, we compare the simulation result of temperature and concentration for 3 points in the test A, B, C. This one, yeah. So this is the comparison result for the temperature for the point A and B and C. So total, so the symbols are the experimental result, and lines with different color is the simulation result. You can see for the temperatures, that one, the simulation match quite well with the measurement, and this is the concentration for the hydrogen by comparing the simulation and the experimental result. So we validated the model, and then we utilize this validated model to do the simulation for the metal hydrogen system. So this is for the temperature distribution, that one, for each reactor. So for each process, that one, yeah. So this is the refrigeration process from A to B, that one, yeah. For each reactor, this is reactor B and reactor A. Reactor A is a low temperature reactor, reactor B is a high temperature reactor, that one, yeah. So from A to B, that one, yeah, reactor B actually is a desorption process, and A is absorption process. A is absorption process, that one, yeah. And you can see the temperature. This is the temperature change, that one, yeah. So that one. So for the desorption process, that one, yeah. The reactor A is desorption process. Yeah, this desorption, and the reactor B is the absorption process. For desorption, you can see at the beginning the temperature suddenly drop and then go up to the heat source temperature. And for the desorption, absorption, the temperature at the beginning go up and then going down like that. Yeah, so you see here go up and down, that one, yeah, and going down and up, that one, for this one, yeah. And also we have some transition process, that one is transition process for from B to C and A to A to D, that one, yeah, to get this. So simply just heat up for both reactors, that one. And for this regeneration process from C to D, you can see that for the reactor A, that one is we call it the absorption process, that one, and the reactor B is desorption process. You can see the temperature similar to the previous one. And the final one is the transition process from C to B and D to A. And this is just to show you the simulation result for the 1/2 cycle, and the next half cycle will be similar. That one result get out. Yeah, this is the result. And similarly for this one shows some more results: temperature, concentration, and also pressure, and also the heat transfer rate. You can see the dynamic operation. So because of time, I don't go to the details. That one, yeah, the details. And we'll just give some result. And we do some we call it effective analysis. That one, yeah, we just change the high temperature heat source temperature between 200 to 230. And we change the low grade heat source temperature from 35 to 50. And we change the medium temperature from 85 to 130. So once we change one parameter, we keep other parameter constant so that we can identify the effect of one parameter on the system performance. For example, this. So the low grade heat source temperature, when you increase that one, so just you can see the COP will increase, and the heat output will increase, and also the heat input will increase as well. For the medium temperature here is just the opposite. For increased medium temperature, that's why COP will decrease, and also the heat source input decrease, and the heat output will decrease as well. And for the effect of high temperature heat source time on the system performance, that one, yeah. So when you increase heat source temperature, high temperature heat source temperature, the COP the heat source input will increase, and the heat output increase. But the COP increase first and then decrease. That means there is a optimal high temperature heat source temperature, so that the COP of the system can be maximized. That one, yeah. So here is the other things I think is similar, so specific heat capacity. So in summary, I think the higher heat source temperature for the low grade heat source temperature can benefit the system performance. And there is an optimum high grade heat source temperature, that one, which can give you a maximum COP. But for the medium temperature, the heat output temperature, the lower the better for system performance. So here we also do some other analysis to optimize system. For example, if we increase the thermal conductivity of thermal metal hydrate, it can, and also increase the heat transfer coefficient for the heat transfer fluid side. So all this can benefit the system performance. And also we analyze also the metal hydrate bed thickness for the system performance. Yeah, the higher the bed thickness will cause the higher, larger cycle point, but it will have a reduced specific heat power. So because of time, I don't go into that details. That one, just give a summary. One metal hydrate pair has been identified for the high temperature metal hydrate heat pump, and the correlation models of PCT phase diagram has been developed to characterize any metal hydrate alloy based on limited measurement data. And the transient CFD model of the metal hydrate heat pump system has been developed. And the metal hydrate heat pumps test rig has been designed and built and allocated in a purposely built hydrogen lab. And the extensive experimental investigation will be carried out. Thank you. Thank you for your attention. Thank you.
Thank you, Professor. Really interesting talk. Thank you very much. Very technical as well, which is nice to see. So any questions anyone would like to ask? I can see typing on the chat, so.
Yeah, I was just wondering, for the medium temperature, why the COP drops? What's the reason? Is it the temperature effect?
Yeah, so if the temperature increase, that one, yeah, so that means the pressure on the high pressure side of the the low temperature reactor will increase. That will reduce the hydrogen transfer from the high temperature reactor to the low temperature. That one, yeah. So yeah, it's similar to the absorption heat pump. If you calculate out the Carnot COP for that, it's similar things. So if you increase the medium temperature, the COP, Carnot COP will decrease. For the actual COP, it's also similar. So for the low pressure side, that one, if you increase that one, yeah, that means because of the direction, the hydrogen flow direction from the low temperature to the high pressure, so it will be difficult for hydrogen to be transferred from the low temperature reactor to the high temperature reactor. That one, yeah. Thank you. Thank you for your question.
Are you going to use the CFD model for other calculations as well later on, or that was just the CFD is finished at the moment?
The CFD calculator has been finished, that one, yeah. But what we need to do, we need to do the validation of the model with our own measurement result.
Okay. Thank you.
Thank you.
Just a question regarding the rig. So just reflecting back on our work, because my PhD was basically rig building and stuff like that as well, looking at metal pipes and their impact on energy performance. What was the main difficulties that you found when it comes to creating the physical model? Because looking back, it was difficult for us to actually recreate the experiment using the rig. So what was the issues that you found when constructing the lab experiment?
The lab, I think the first thing is what we found. We designed the reactors. I think design the reactor is quite a difficult thing. That one, yeah. So you have to find out the metal hydrology first, and then based on the operating conditions, that one, yeah, and to calculate out the weight of the metal hydrology to be charged in the reactors, and also design the reactor based on the operating temperature and the pressure, and also the available. We need to utilize a filter to be installed in the metal reactor. So if the filter is available or not, so and what type of filter can be used. So which all can affect the design of the reactors, and also the test rig development and also assemble. It's not an easier job to do. And also because test rig is related to the hydrogen, that one, yeah, safety and healthy issues are quite important. And it's not easier. Once you develop the test rig, you can't operate directly. You have to do a lot of workshop, because the hard job and also other things. And once everything is ready, you can start to do the measurement. And also that you need to have a proper, I think, purposely built hydrogen lab, so that you can't simply put the rig to anywhere. So you have to put it into the test rig lab, so that it can operate safely.
Yeah, that makes sense. I could imagine also with the the temperature that you're dealing with, especially the high one, it must be a challenge to even just to control these parameters at those
and also the
temperatures.
controls. So yes, it's a challenges here.
Perfect. Yeah, perfect. Any questions? I see there's typing in the chat, so we'll hopefully a question will come up. So just wondering about also this like scaling up of it. What would be like the challenges of like scaling it up on like an actual, urban planning scale?
Yeah. So depending on the applications, I think first we need to know the heat output, and based on that we can design the scale up system, that one system, and also we need to design a larger size of reactors, that one, yeah. So to make it suitable for the actual application.
Okay.
Yeah.
Thank you. Thank you very much.
Thank
Okay,
you.
that's my question. I love experimental rigs, so that's why I'm focused more on that. Thank you very much. No questions on the chat, so thank you very much for your time. Very, very interesting, relevant talk.
Okay.
Really
Okay, thanks.
enjoyed it, and now considering to come to South Bank to see it in person.
Okay, you're welcome.
Yeah.
Everyone is welcome to come to visit us.
Thank you.
Yeah.
No, I really
Okay,
looking
thanks
forward to it.
thanks everyone. Thanks everyone for your sharing. Yeah.
No, thanks for your time.
Okay.
The recording will be